interesting now. So just to review where we've got to last time, we got to this decomposition of forms on an almost complex manifold. So the idea is that an almost complex manifold, remember, was just a smooth manifold equipped with this operator J on the tangent spaces, which squares to minus the identity. And that implies that your manifold had to be even dimensional. In fact, you could find a basis for each tangent space that looked like this. And it's called an almost complex manifold because it's not quite the same thing as a complex manifold, as we'll discuss in a second. Slightly weaker than a complex manifold, but even on an almost complex manifold, your forms decompose like this. So what we found was that if you look at the top exterior power of the complexified cotangent space, then it's going to split into these A, B components, right? So here we're looking at a four-dimensional real manifold, which had a almost complex structure on it. And for example, the two forms locally were looking like this. And yeah, I should be a little bit careful here. I talk about dz and dz bar. And if I'm doing that, then I'm actually, what do I mean? Am I saying that z is actually a coordinate? That's a bit naughty. I just mean that the basis dual to the del x and, to the del x plus I del y. So in other words, just to be clear here, what do I mean by dzi here on an almost complex manifold? I don't mean d of a function because there aren't necessarily holomorphic charts, right? I actually just mean just dx plus I dy. Okay. It's a little subtlety there, but just so that we understand that we're working on a real manifold equipped with an almost complex structure, but we still get this decomposition of the cotangent spaces and as shown. And so that means that the K forms are going to decompose into these subspaces. So you can talk about the A, B components of a K form on an almost complex manifold. So that's what we did last time. Okay. So let's carry on now on this theme by comparing almost complex to complex manifolds. So the question that we want to answer now in this first hour is, when can we upgrade an almost complex manifold to an actual complex manifold? What do I mean by that? So just recall, an almost complex manifold is a smooth manifold equipped with some structure, namely on each tangent space, we have this operator which squares to minus the identity. And I want to point out this is an infinitesimal structure. In other words, it's a structure that's living on the tangent spaces of the manifold. On the other hand, what is a complex manifold? It's something that's been equipped with a topological space equipped with a holomorphic atlas, right? Which means that you've actually got local charts. So around each point X, you can find a open set U and a homeomorphism from that open set into the CM. And that's actually going to give you these holomorphic coordinates, Z1 up to Cm on your manifold. So as opposed to a complex structure, this is now a local structure in the sense that it's living on open sets, whereas this thing was living on the tangent spaces. So this is a stronger thing than this, all right? So the question is, we know that given one of these, you definitely get one of these, because you can always, on the Z's, you can just, each Z can be written as X plus IY, and you can just send del X to del Y and del Y to minus del X. So that gives you an almost complex structure associated to every complex manifold. The converse is what we're asking. We want to know, given one of these guys, when can I upgrade it to one of these guys? In other words, when can I actually find holomorphic atlas in such a way that the underlying almost complex structure of the holomorphic atlas is my original one that I started with? Right. So a related question, as we'll see, is following. So we've seen that the complex valued K-forms on every almost complex manifold decompose like this, right? Into, just as I said, on any complex manifold, the almost complex manifold, the K-forms decompose into their AB components. And the question is, how does the exterior derivative map get along with that decomposition? So we know the exterior derivative map is a map from K-forms to K+1 forms. And that's true if you're looking at real valued forms or at complex valued forms. You can just extend it by complex linearity. So we've got this map that we defined quite a long time ago. But how does that respect this decomposition on the space of K-forms on an almost complex manifold? It turns out that these two matters are the same question. So to answer this, we're actually going to need to know some material about vector fields that I skipped earlier in lectures 1 and 2 when I was going over smooth manifolds. So there was some material that we do need to know if we're going to answer this question now. So let's cover that material now. So recall that for us, a vector field is a smooth section or a smooth selection, shall I say, of a vector at every point P in the tangent space of the manifold at P. Okay, and what is the tangent space for us? Tangent space is defined, sorry, I should say a vector in the tangent space is defined as an equivalence class of curves going through a point in a manifold, right? So here's a manifold M. I'm trying to define the tangent space at P. So I need to define what an element of the tangent space is. And an element of the tangent space is a curve, or an equivalence class of a curve, a smooth curve, going through the point P. And I say that two smooth curves are equivalent if, when I use the chart, and then I map that curve to a chart in Rm, then I can actually compute the derivative of that curve at 0. That's going to be an actual column vector in Rm. And two curves are considered equivalent if they have the same derivative at 0 in a chart. Okay, so that's how we were defining our tangent space. And in particular, every vector field on X, or every vector field X on our manifold, gave us a linear operator, which I'm also going to call X for convenience, which is a map from the smooth functions on M to the smooth functions on M. The linear operator from this space, vector space to itself, right? The space of all smooth functions is a big infinite dimensional vector space. And a vector field, in the sense I've defined it here, gives us a map from smooth functions to smooth functions by differentiating along the vector field. So how is that defined? Just to be clear, I start with the smooth function f. I want to differentiate it along the vector field x to get a new smooth function. The value of that new smooth function at P is defined to be the derivative of my function along the curve gamma, which represents the vector x at P. Okay. So we're differentiating the function along this curve at t equals 0. And then at each point P, we've got such a curve, and so we can differentiate the function along that curve. So that's how we get a map from functions to functions given a vector field in the sense that we defined it. And if you think about it, this map from functions to functions, it's not just going to be any old linear map. It's going to satisfy the Leibniz rule, which is basically the product rule from calculus, right? If you take two smooth functions, f and g, and you multiply them together, and then you differentiate along the vector field x, because you're doing this derivative here, you're going to be calculating the derivative of a product of functions. So it's going to be the derivative of the first times the second, plus the first times the derivative of the second. Okay. And actually, this gives us an alternative operator theoretic way to define vector fields. So we have this lemma, which is that a smooth vector field on M, in the sense I was defining it, namely a smooth selection of a vector in the sense of an equivalence class of curves at each point of the manifold, is actually the same thing as a linear operator from smooth functions to smooth functions, which satisfies the Leibniz rule. So this thing here actually characterizes the vector field uniquely. That's quite elegant. I've shown you the one direction, how to start from a vector field in the sense we define it and get one of these linear operators. Conversely, given a linear operator satisfying the Leibniz rule, you want to construct a vector field in the way we defined it. And that requires sort of like a fundamental theorem of calculus. So a nice exercise to fill in the details of this proof and just compare with Luyenda proposition 2.1, where he does formulate it slightly differently. Any questions so far? Right. So that's the one concept we're going to need, is the idea of thinking of a vector field as an operator from functions to functions. Thanks. And why do I want that? Is because this operator theoretic viewpoint is very useful for Lie brackets. So what do I mean by Lie bracket? So given two smooth vector fields on a manifold, remember, don't worry about complex manifolds, forget about that now, we're just back to good old smooth manifolds. And I've got a smooth vector field X and another smooth vector field Y, and I can do this operation to give me a new vector field called the Lie bracket of those two vector fields. The cool thing is, if I want to define a vector field, I can just define it as a map from smooth functions to smooth functions, satisfying the Leibniz rule. So, and here's the formula. I say that the Lie bracket of X and Y, when operating on a function f, is given by first you apply Y to f, and then you apply X. You subtract that from that, what happens when you first apply X and then apply Y. So it's like the commutator of the operators. And of course, we need to check that this right-hand side is actually a vector field. In other words, the way we're defining vector fields are things which are linear operators from functions to functions which satisfy Leibniz. So I have to check that. In other words, I have to check that this formula is going to satisfy Leibniz. That's a good exercise. Once you know that it does, then you know that it is a vector field. Okay. How do I geometrically understand what this Lie bracket is doing? I'm not going to go into this. We're not going to need it that much, but it's important to have a picture. So the Lie brackets of two vector fields at a point P measures the change in the one vector field as we move along the integral curves of the other vector field. Okay. So just the picture there is this picture. Maybe I can do a little trick here. I'm not sure if this is very useful. Okay, so it's just the picture here is that you've got a vector field X, and we didn't really speak about this concept, but when you've got a vector field, then you can flow along the vector field. Sort of like at every point you have the integral curves of that vector field, which is a curve whose tangent vector at each point is the vector field itself. So as I flow along X, I can ask myself, I wonder what is happening to the vectors Y as I flow along X. So I can differentiate Y as I flow along X. And that's actually what this thing is measuring. And alternatively, it can be thought of as differentiating X as you flow along Y. Okay. Anyhow, what you need to know is just that we've got this nice definition for it as a commutator. And this Lie bracket of vector fields also gives us a new coordinate-free way, not coordinate way, but a coordinate-free way to define the exterior derivative of differential forms. Right, so recall that currently our formula for how to calculate the exterior derivative of a K-form is like this. Sorry, okay, this should be summing up to M, the dimension of the manifold. So what you do to apply the D operator, the exterior derivative operator, you sum over all the directions in the manifold, and then you differentiate the component function of the K-form in that direction, and then you shove a little dx relative to that direction in front, dx wedge, whatever was remaining. Right, remember we did this back in lecture 2. So just to recall, so if you had a K-form, if you want to compute D of that K-form, that's going to give you a K+1 form. Where you did it was you chose a coordinate chart locally, so that you got some coordinates, x1 up to xm, and then that means you could express your K-form like this. It's going to be the sum of some component functions. These things aren't just numbers, but they're functions of x times these wedges of the dx's. So there's k of these altogether. That gives us a K-form. And I want to calculate d of omega. So the way I do it is I use this mnemonic here. So d of omega is you sum over all the directions in the manifold. So there's m of them. For each direction, you differentiate this component function in that direction, and then you put a little dx of that direction wedge the rest in front. So this is the stuff that I'm adding there. Remember, we then proved that d squared equals 0. But anyway, this is a nice little operation, and we even saw what it looked like in R3. I'm just reminding you how we calculated, but you note that there is one sort of weakness of this definition. It's very explicit, but weirdly it did require you to have a coordinate chart, and then so we had to work this thing out relative to a coordinate chart. Although the answer didn't depend on the coordinate chart you used, that was also an exercise. We didn't need the coordinate chart to work it out. So it would be nice if there was a formula that didn't make explicit reference to the coordinate chart. And that's what this Lie bracket of vector fields is going to allow us to do. Okay, it gives us a coordinate-free formula for the exterior derivative. So instead of this formula here, which uses coordinates, I'm going to write it down like this. See, I've got a K-form. So I'm going to calculate what d of omega is. It's going to be a K+1 form. What is a K+1 form? It's a machine which eats up K+1 tangent vectors at each point and spits out a number. So here are your K+1 tangent vectors. There's x0, x1, dot, 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 up to xk. There's K+1 of them here. So I have to say what d omega does to these vectors. These are just arbitrary vectors. They've got nothing to do with a coordinate chart. They're just arbitrary vectors in the tangent space at each point. And I need to say what the K+1 form is going to do when it eats them up. I have to calculate a number now. And this number is calculated as follows. I sum over all the directions in space with a minus sign in front. And then I take that vector and I differentiate this function in the direction of that vector. What is this function? It's the function which is obtained by taking my original K-form omega and applying it to the remaining K vectors when I remove xi. So that's what this hat means. It means remove xi from the list, and then the remaining K vectors, we feed them to omega to get us a number. So omega is something which eats up K vectors and spits out a number. So this is a number at each point. So that means it's a function on the manifold. I can differentiate that function in the direction of the vector xi. That's what this thing here means. Okay, so that's this section of the formula. Then I've got another section here where there's a double sum over I less than j of what? Well, I take my original K form omega, and I feed it K vectors as follows. I take my original K plus 1 vectors that I'm given here. I remove the ith and the jth vector from that list. So then I've got K minus 1 vectors. And in the beginning of the list, I insert this new vector, which is the Lie bracket of xi with xj. So at each point, xi, so yeah, these were sort of vector fields defined locally. So at each point, I've got this Lie bracket, and that means I've got this vector at each point. So I can feed that into the first slot of omega. Right, so it's quite it's a beautiful formula, and yeah, it reminds one of the if you guys have seen, I know Dario has seen quite closely the what's it, the R map in Hopf-algebras. Forgot what it's called now, but the braiding operator. You have this R subscript IJ thing that you do. I'm just mentioning that to you, Dario, that this part of the formula here is very much like a sort of a RIJ acting there, which is sort of actually, it makes sense actually, because this differential forms does act in a way like a braiding. You can make that rigorous. Anyway, this is a beautiful formula, and then the exercise is, I'm not going to ask you to prove that this formula is the same as this formula, because that requires a bit more calculations. So, but I just want you to at least check that this formula at least agrees with this formula in a coordinate chart. I would have to check. I mean, I would check some more things here as well. Like I would have to check like the invariance of this formula. But you should be able to at least check that it agrees with this formula in a coordinate chart. So in other words, when the vectors that I feed it are my coordinate vector fields, then I want to recover this formula. Okay. So we've introduced, what have we introduced? We've introduced the operator theoretic way of thinking about vector fields. We did that so that we could talk about Lie brackets of vector fields. And we did that so that we could talk about the coordinate free way to speak about the exterior derivative map. And we're now ready to give the answer to our first question we raised at the beginning of the lecture, which was, when can an almost complex manifold be upgraded to a complex manifold? So when can you actually provide these holomorphic charts for the manifold, for the almost complex manifold? And that theorem is called the Newlander-Nirenberg theorem. And it says that an almost complex manifold can be upgraded to a complex manifold. In other words, it can be equipped with a compatible holomorphic atlas if and only if this almost complex structure J is integrable. What does integrable mean? For our purposes, it simply means this. Means that if you start with two smooth vector fields that are of type 1, 0, right? Remember, each tangent space, when you complexify it, decomposes into these different parts on an almost complex manifold. And so I can talk about a smooth vector field of type 1, 0 or type 0, 1. So if I take two vector fields of type 1, 0, and I compute their Lie brackets, then I also want to get a vector field of type 1, 0. If that's always the case, then we say that the almost complex structure J is integrable, and the theorem says that if that's the situation, then you can actually find this holomorphic atlas. Okay, any questions about that? So I'm not going to prove this. But it's sort of a thing that we're just going to take on faith. But it's a nice statement tells us exactly when an almost complex structure can be upgraded to a complex structure It's got to do with calculating these Lie brackets. You see, the Lie bracket of x and y is going to be a vector field. So it's going to have components that are type 1, 0 and type 0, 1. Because every vector field can be split up. Every vector field decomposes into its 1, 0 part and a 0, 1 part. So in general, this guy, if you start with a vector field of type 1, 0, and you do a Lie bracket with another vector field of type 1, 0, what you're going to get out is some smooth vector field on your manifold. So it's going to have a 1, 0 component and a 0, 1 component. But what we're asking is that there isn't a 0, 1 component, that it only has, that when you take two vector fields of type 1, 0 and you Lie bracket them together, you get back only a 1, 0 vector field out. And then that's what it means to say that the almost complex structure is integrable. And the theorem says that in that case, you can actually find holomorphic charts for the manifold. So that's the hard direction. But the easy direction is, given the fact that you've got holomorphic charts, then this is going to be true. And the easiest way to see that is because you've got these holomorphic charts, you could just locally write down the expression for what the commutator does. And because the commutator would then be calculated by differentiating with respect to the z's and the z bars, because you've got this holomorphic charts. And so that's why you'd easily see that this is the case. If you don't have the holomorphic atlas, then you don't have these coordinates. So you can't differentiate with respect to coordinate charts. Okay, so we can also give the answer to our second question about how the exterior derivative interacts with the decomposition of K-forms on a manifold. Remember, I asked in the second question, how does the exterior derivative map tie in with the decomposition of K-forms on an almost complex manifold? And here's the answer. If you've got an almost complex manifold, then the following are equivalent. Firstly, that J is integrable, which, as we know from the Newland and Nuremberg theorem, means that it can be upgraded to an actual complex manifold. So that's equivalent to saying that when I apply the exterior derivative operator to a 1, 0 form, that what I'm going to get out is going to live only in this subspace. And remember that there's one part I'm leaving out here, which should be the 0, 2 subspace. All right. So I'm saying that the components, if you start with the 1, 0, a form of type 1, 0, and you compute its exterior derivative, then you're going to, the result will have 0 in its 0, 2 component. That's what I'm saying. It'll have other stuff, but it won't have a 0, 2 component. And that turns out that if that's the case, then that's actually equivalent to being integrable. And then, moreover, if this is holding on 1 forms, then it's going to hold on general forms. Okay. So that the D operator is going to send a P, Q form to a combination of a P plus 1, Q form and a P, Q plus 1 form. So it's either going to raise P or raise Q by 1. Only 1. Okay. So let's have a look at this. This one we can prove. Okay, let's see how we'll do this together. Okay, so let's show that 1 is equivalent to 2. So suppose I start with a 1, 0 form, omega. Okay, so I'll start with one of these guys. And also let x and y be smooth vector fields of type 0, 1. omega is a 1, 0 form, and x and y are 0, 1 vector fields. What do I know? Well, if I calculate d omega, it's going to be a certain 2 form on the manifold, right? Because omega was a 1 form. And if I calculate d omega, that means it's a 2 form. So I can ask what happens when I feed it two vector fields. It's a 2 form, so it eats up 2 vector fields to give a number. So when I feed it these 2 particular vector fields, these are vector fields of type 0, 1, what's going to happen? Well, I can now go use my coordinate-free formula for the exterior derivative. So I'm applying this now to the case of a 1 form. So it tells me that d omega is going to be a 2 form. It's going to eat up a pair of vector fields. And the way I have to calculate it is I'm going to get this contribution plus this contribution. So let's do this first contribution. I have to sum over the number of vectors that I have. I've got 2 vectors. And for each such vector, I have to remove that vector and then apply omega to the remaining vectors. And I've got to differentiate the result in the direction of that vector. So I think you'll agree with me that that first part is going to be vector x applied to omega of y minus the vector y, the vector field y applied to omega of x. Right? That's this part here. And then I've got this part here where I've got to remove 2 vectors. And the only vectors that I can remove are x and y. So there's only a single contribution. And then I've got to calculate this thing here. So since I've removed those 2 vectors, the only remaining vector is just their commutator. So I'll now add on this term here, omega applied to the commutator of x and y. Okay. Any questions? Because that's the key first step, right? And now we have a look here. What's going on? Omega was of type 1, 0, and is being fed vector fields of type 0, 1. So that means it's going to be 0 on those vector fields, right? Because a 1, 0 form, when you feed it a 0, 1 vector, gives you 0. Similarly here, you're going to get 0. So the only thing that remains is this part here. And I think I've left out a minus sign here, so this should be a minus. So I get minus omega applied to the commutator of x and y. Okay, so what do we conclude from this? We conclude that to say that d omega is applied to x and y is 0, that's equivalent to saying that when I calculate the commutator of x and y, and I calculate its 1, 0 components, that's got to be inside the kernel of my 1 form omega, right? I think that's what this theorem is, or this little calculation here is saying that this guy is going to be 0 if and only if omega applied to this commutator is 0. And omega applied to the commutator is 0 if and only if, when I calculate the 1, 0 component of the commutator, that part has to be 0. See, I know that omega definitely vanishes on 0, 1 forms. So the question is what's going to happen to the 1, 0 component of this? Okay. So let's see. So that means that when I start with a 1-0 form, and I want to know whether I'm going to get out something that lives in just in 2-0 forms and 1,1 forms. So notice I'm leaving out the 0,2 forms here, right? So if that's the case, which is the thing that I'm trying to investigate, that's this claim here, which is claim 2. So this is the case if and only if for all x and y in smooth sections of the 0,1 vector fields, 0,1, all x and y being 0,1 vector fields on M, we have that commutator of x and y, its 1,0 component is equal to 0. In other words, the commutator of x and y is again a 0,1 vector field. Okay, so I've therefore proved that this condition 2 is equivalent to this condition 1. Because I've shown that this statement here is equivalent to the statement that if you start with 2 vector fields of type 0, 1, and you calculate their commutator, then you're going to again get a vector field of type 0, 1, which is exactly the statement that the complex structure is integrable. Of course, when I spoke about integrability, I said the other way around. I said you start with 2 1-0 vector fields and you calculate their commutator, you want to again get a 1-0 vector field. But that's equivalent to saying if you start with 2 0-1 vector fields and you calculate the commutator, you must get back a 0-1 vector field. Okay, so I've shown that 1 and 2 are equivalent. Any questions there? Give myself some more space here. Okay, so let's prove that 2 and 3 are equivalent. So that's saying that when I apply D, number 3 is saying when I apply D more generally to a P, Q form, I want to get a P plus 1, Q form or a P, Q plus 1 form and nothing else. Because in principle, I could get out also a component in the P plus 2, Q minus 1 and so on, right? I don't want any other components. So I have to check that this is equivalent to this. Clearly 3 implies 2 because 2 is a special case of 3. So I want to show that 2 implies 3. How do I do that? Well, this is actually just going to follow from the Leibniz formula. For D on K forms. It's right about this is an exercise. What number are we on now for this section? We're on exercise 4. Okay, so just, I don't think I mentioned this when I spoke about the exterior derivative, but if you start with a K form on a manifold, and let's say you start with a K form and a, okay, let's write like this. I've got a K form, and then I've got a L form. You know, what I'm wanting to do is get a sort of generalization of the product rule. That's going to, product rule is something that happens when you multiply 2 functions together and you differentiate. I want to know what happens when you wedge 2 forms together and you differentiate. Remember, a function is just an example of a 0 form. So now I'm going to say, okay, what happens more generally when I wedge a K form with an eta, with a L form together? What happens when I differentiate that? And if you go back and you just look at the definition of how exterior derivative works, it's going to be the same as first applying D to the first form, and then wedging it with the second, plus, now you see, heuristically, this D is going to hop over the omega and act on the eta. And omega is a K form. So I have to hop over K sort of things. So I'm going to pick up a minus sign, which is going to have K minus signs. So then I'm going to go omega wedge d eta. That's the Leibniz formula. And that's how you're going to be able to prove this exercise, because you see, we can locally write a P comma Q form as a sum of a bunch of wedges of P wedges of the DZs and Q wedges of the DZ bars in each tangent space, where Z and Z bar, again, defined not as coordinate charts, but as that almost complex manifold way. And so then I can apply D to that, and so I can use the Leibniz formula. In the end, proving 3 is going to boil down to proving 2, because I'm differentiating some big product, and eventually I just need to know this. All right, so there, that's nice. We've now solved the questions that we wanted to solve. And let's see. Maybe let's just finish with this. So let's just remind ourselves where we were, where we started this lecture on. The question was, when can we upgrade an almost complex manifold to a complex manifold? And the answer turned out to be related to how does the exterior derivative map relate to the decomposition of K forms on an almost complex manifold. And the complete answer was given over here, namely that an almost complex manifold is integrable, meaning that if you start with a 1,0 vector field and another 1,0 vector field, you calculate the commutator, you're going to again get a 1,0 vector field. And the Newland and Nuremberg theorem says that if that's the case, then that's equivalent to saying that the almost complex structure can be upgraded to a complex structure. So this is the condition we seek. And it turns out that that condition is equivalent to a condition about how the exterior derivative operator gets along with this decomposition of forms. It says that when you apply D to a 1,0 form, you get a 2,0 form and a 1,1 form as components, but you don't get a 0, 2 components. Okay, so more generally, when you apply it to a P, Q form, you're going to get components just of 2 types. One where you've increased P by 1 and one where you've increased Q by 1. But you won't get any other types, right? Because there's a bunch of other types here as well. I could have increased P by 2 and Q, and then I would subtract Q, 1 from Q and so on. That would all wedge together to get a P plus Q plus 1 form. But I'm saying that those parts are 0. Okay, so as a corollary here, we see that every 2-dimensional almost complex manifold, 2-dimensional in terms of 2 real dimensions, is actually integrable. So we never have to worry about this problem for 2-dimensional almost complex manifolds, because we've always got to have that when I take a 1,0 form on a 2-dimensional real manifold and I calculate its D, well, I have to get out a 1, 1 form, because in principle, what am I going to get out? In principle, I know I'm going to get out a 2, 0 form, plus a 1, 1 form, plus a 0, 2 form. The reason is because this guy is a 1 form, so when I calculate its D, I'm going to get a 2 form. And the 2 forms split into 3 subspaces. But now if I look at these 3 subspaces, this subspace here is 0. And this subspace here is 0. Because, as we saw when we were doing our example on a 4-dimensional manifold last time, remember, some of these spaces turn out to be 0 because you can't like wedge 3 DZs together. In our example, locally, the cotangent space is going to have a DZ and a DZ bar. And to get a 2, 0 form, you're going to have to do a dz wedge dz, and that's going to be a problem. Okay, so that's going to be a 0. So there isn't a 2, 0 form, just sort of by dimension reasons. There isn't a 0, 2 form, and therefore we know that this part is 0 and this part is 0, and all I wanted was that d of a 1, 0 form was going to land in here. And I've definitely got that, because in fact it lands in here. All that I wanted was that this part was going to be 0, and definitely is 0, just for dimension reasons. Okay, that's kind of cool, right? So in particular, every surface, which is the way that I visualize sort of surfaces, I think of them as living inside 3 dimensions, like a torus or a sphere or a donut. So every such surface embedded in R3 has a canonical complex structure. There's actually canonical complex coordinate charts that we can place on such a surface, which I think is very beautiful, right? So just remember, why is that the case? Well, because every surface embedded in R3 has a canonical almost complex structure. Because on each tangent space, we can rotate by counterclockwise by 90 degrees. Remember, that was an example we did in the second lecture, right? I started with this example. I said, suppose you've got a smooth oriented surface embedded in R3, then on each tangent space, you can rotate counterclockwise. You know what counterclockwise means because it's orientable by 90 degrees. And obviously doing that twice is going to give you minus the identity. And then I also went further and I asked, how do I actually write down, could I possibly write down holomorphic charts for this J, right? And so I was sort of jumping the gun there. I was trying to already figure out what are the associated complex coordinates. And there's a nice geometric fact, which I mentioned last time, was that there is a natural map whenever you've got an embedded surface. You always have a natural map, the Gauss map, from the surface into the 2-sphere, which just sends each point to the outward unit normal at that point. It's called the Gauss map. And it turns out that the Gauss map is holomorphic as a map between almost complex manifolds if M is a minimal surface. So M has to be a certain kind of surface. No, it doesn't have to be, but if M is a certain kind of surface, then you're assured that this Gauss map is a holomorphic map, which means that's the Gauss map would then provide you with holomorphic charts on M. What does it mean to be a minimal surface? It means that the shape operator on the tangent space, by definition, it's an operator from tangent space to itself. It takes a vector in the tangent space and differentiates the normal vector along that vector. So along a certain vector, you can see what happens to the normal vector, so you can differentiate it, and that the derivative is going to again be in the tangent space, and then that's what the shape operator does. And so that's going to give you a map from the tangent space to itself. You can diagonalize that map and calculate its eigenvalues, and in order for this M to be a minimal surface, the definition is that the eigenvalues must come in opposite pairs. So you must have plus K and minus K, or plus kappa and minus kappa. Those are called the principal curvatures. General, those will just be 2 different numbers. Like for the 2-sphere, for example, they're both 1 and 1. That's an indication that the 2-sphere is positively curved. But for a minimal surface, one of them is going to be plus. In a certain direction, it's going to be positively curved. And the other direction is going to be minus. In that direction, it's going to be negatively curved. Okay, and they're actually going to be opposite in magnitude. If that's the case, then this Gauss map is a holomorphic map. It's not the only way that you can get a holomorphic chart, but it's just an interesting differential geometry situation, which I kind of like. So just to get back to our statement right now, yeah, so we've just seen that every surface embedded in R3 has a canonical complex structure. And reason being that we know we've got a canonical almost complex structure, and we know that it will upgrade to a complex structure by this theorem that we just proved. And here's a puzzle for you. which I would like to know the answer to, and I haven't seen the answer written down somewhere, so someone can show me or else work it out. To describe geometrically the holomorphic coordinates on such a surface. We know they exist and they're canonical up to equivalence. To describe them geometrically, we know how to do it for a minimal surface. I showed you just now we could just use the Gauss map. But if I just give you some random surface, for example, like a torus, what are the coordinate charts there? And just to be more specific, so consider the round torus in R3. That's my sort of two spheres, my favorite manifold, and in R3, and then my second favorite would be the torus, right? So the round torus T subscript A comma B, it's got a circle of radius A that's being swept around another circle of radius B. Okay, clearly B has to be bigger than A, else this doesn't make sense. And what do we know? We know that it's a complex manifold of genus 1. And although I haven't proved this, every such complex manifold of genus 1 meaning it's got a single hole, is holomorphically diffeomorphic to the quotient of the complex plane by a lattice. And you might as well take the lattice to have generators 1 and tau, where tau lives in the upper half plane. See, here is the generators of the lattice, the complex number 1 and the complex number tau. So these two numbers generate a lattice in the complex plane. I can take the quotient of the complex plane by that lattice, as we saw last time. That gives us a complex manifold. And I know from abstract principles that this complex manifold, which I've just defined above, must be holomorphically diffeomorphic to one of these guys for some tau. And the question is, determine tau as a function, as an explicit function of those radiuses A and B. It's a puzzle for you, please. Yeah, a puzzle for me as well. Let's take a break then, but any questions? Okay, so thanks, Dario. So let's take a 10-minute break, and we'll be back at 3:05. All right, cool. Let's carry on. So yeah, we're firmly into the book of LeFloc at the moment. So you'll notice, I think we're sort of on chapter 2.4 of LeFloc now. All right. So where are we? We have discovered something interesting about complex manifolds, and namely, let's just do this trick here. So we've discovered that on a complex manifold, we have local holomorphic coordinates, Z1 up to Zm. Obviously, we knew that. And we also knew that a P, Q form locally looks like this. This is something that we did last time, right? So this is a form of type P, Q. That means it's going to locally be a wedge of dz, P dz's and Q dz bars. And the P plus the Q, yeah, well, there's no condition on that. So there's P dz's and Q dz bars. These z's now are actual functions that we have. These are our coordinates because we're on a complex manifold now, not an almost complex manifold. And then of course, so these are the sort of basis vectors, and then you can at each point multiply them by a number, so you can get an arbitrary smooth function locally that's multiplying these basis vectors. That's going to be what a P, Q form looks like. These are arbitrarily smooth, complex valued functions. Traditionally, if your function is a smooth, complex valued function of a single complex coordinate, then you write that as a function f of z, z bar, because it's sort of depending on z and on z bar. If it's a holomorphic function, then it's only going to depend on z, not on z bar. But if you got a function z, z bar, then that means it's an arbitrary smooth function. Okay. So that's what a P, Q form locally looks like on a complex manifold. And when I calculate d of omega, when I calculate the exterior derivative, you might as well use these holomorphic coordinate charts now. So then that's going to then split up into the parts where you're differentiating in the z directions and the parts where you're differentiating in the z bar directions. Okay, so in other words, let's say it again in a different way. The exterior derivative map, we know, is a map that increases the degree of a form. So if you start with the P, Q form, we know we're going to get a form that's of degree 1 higher, and we know we're on a complex manifold. So we agreed that on a complex manifold, we had this theorem, which said that, in fact, that means that when you calculate d of a P, Q form, you're going to get out a P plus 1, Q form components and a P, Q plus 1 components, but nothing else. So, so since that's the case, that means we can decompose the exterior derivative map on a complex manifold as the sum of del, just to say how you pronounce this, this is del, D-E-L, del plus del bar. And the cool mnemonic fact is that this was discovered by a Frenchman called Dolbeau, which sounds a lot like del bar. Anyway, these are called the Dolbeau operators, del and del bar. So we, on a complex manifold, we decomposed the exterior derivative as a sum of del plus del bar, right? Where del bar is going to pick out this component, and del bar is going to pick out this component. In other words, del is you apply D and then you project onto this component. Del bar is you apply D and you project onto this component. Okay, so we have a finer control of the exterior derivative map on a complex manifold because it decomposes into these two pieces. And that's the fundamental utility that complex manifolds give us. We couldn't say that on an almost complex manifold, because on an almost complex manifold, all we could say is that when I differentiate a P, Q form, I'm going to get a whole bunch of components out. So I couldn't decompose it this way, or I could actually, but then I would have to write down a bunch of other components here, and it wouldn't be very useful. But on a complex manifold, I've just got these two components. So here's a nice little lemma. So just to set the scene for our notation, so suppose you've got a smooth complex valued function on a complex manifold M. Then the following are equivalent. The first is that the function is holomorphic. Remember what that means? It means that locally you can find a chart such that the function is holomorphic in that chart. The second condition is that del bar applied to F is 0. So this is going to be a certain form, a one form of type 0, 1, because that's what del bar does to a 0 form. It increases the second component by 1. So you'll start off with a 0, 0 form. That's what F is, the 0, 0 form. And when I apply del bar to it, I'm going to get a 0, 1 form. And the claim is that when I calculate that 0, 1 form, that 0, 1 form being 0 is equivalent to saying that the original function F is holomorphic. And then the third equivalent condition is that for every smooth vector field of type 1, 0, this is when I take the complex conjugate of that, and I call that Z bar, so that should be a vector field of type, this guy here is a vector field of type 0, 1, right? Because I've taken this 1, 0 vector field and I've conjugated it, then you get a 0, 1 vector field. So when I apply an arbitrary, another way of saying this is that when I apply an arbitrary 0, 1 vector field to F, I get 0. But I wanted to write it in a way that was notationally similar to this, so that's why I wrote it like this. Okay. So let's prove this. Okay, so let's prove that 1 is the same as 2. So when I calculate del bar F locally, I'm going to get, in terms of the local coordinates, by definition, I've got a sum over all the directions, and I'll get del F by del Z I bar Z I bar, right? Everyone agree with that? That's how this del bar operator works. It's exactly this piece over here. Okay. So what does that mean? It means that this guy is going to be 0, which is condition 2, if and only if derivative of F in the Zi bar directions equals 0. Okay, and that's exactly the statement that F is holomorphic, right? Well, you might say, what does it mean to be holomorphic? We define holomorphic as something that, for a holomorphic function of a single variable, something that satisfies the Cauchy-Riemann equations. And that's equivalent, as you know, to saying that the derivative of F in the Z bar direction is 0. Okay, so that's what I'm saying here. So that shows that 1 is equivalent to 2, and then 2 being equivalent to 3. Well, what is Z bar of F by definition? So that's this vector field applied to this function. By definition, you can calculate that as df evaluated on z bar. And since z bar is a vector field of type 0, 1, when I calculate df, I'm going to get a vector field of type 0, 1 and 1, 0. The 1, 0 part it will always eat a 0, 1 part and give me 0. So I don't have to worry about that part. So in other words, df evaluated on a 0, 1 vector field is the same as del bar f evaluated on a 0, 1 vector field, because certainly del f acting on z bar will be 0. So I don't have to worry about that part. So in other words, del bar f equals 0. That's what this is for all 0, 1 vector fields, if and only if for all, exactly the statement here. So okay. Yeah, any questions there? Nothing deep going on there, but just make sure that we are all on the same page. 3 different notational ways to say that a certain function is holomorphic. And these characterizations would actually then extend to higher degree as well. Okay, so let's do another little demo. Do I have that chat? Sorry, give me for a second. Right, so let's do this other lemma quickly first. So the lemma is that if I do del squared, then I get 0. I know that d squared is 0, but now I'm saying that del squared is 0 as well. And I'm also saying that del, if you do del bar and then you do del, then you won't get 0, but you will get minus what will happen if you first do del and then del bar. And I'm also saying that del bar squared is equal to 0. Okay, so this recall that d squared is equal to 0. So now I've got a refinement of that at the level of the del bar operators. So at the level of the exterior derivative operator, all I can say is that d squared equals 0. At the level of the del bar operators, I've got a refined set of equations. So let's prove this. Well, I know that d is equal to del plus del bar. So that means that d squared equals 0. Then that means that del plus del bar squared is equal to 0. And what is this? This is going to be del squared plus del bar plus del bar del plus del bar squared. Now let's draw a little picture here. We've got our P comma Q forms. And let's see what's going to happen. When I do del to it, then I'm going to get into P plus 1 comma Q forms. When I do del bar to it, I'm going to get into P comma Q plus 1 forms. When I do del again to one of these, I'm going to get to a P plus 2 comma Q form. Or I could do del bar to this, and I would get into a P plus 1 comma Q plus 1 form. Similarly, if I'm over here, and I could do a del to that, so I could do it, then I would again end up in a P plus 1 comma Q plus 1 form. Or I could do a del bar, and then I would get to a P comma Q plus 2 form. Okay, so that's what we're saying here. Excuse me. So del squared is this composite here. And so this sum of terms is 0. So what is that telling us? Since they're living in different subspaces, that's telling us a lot, because that means that this whole combination here is 0, which means that each of its components must be 0. So this is the only component that's living in here. So it has to be 0. And this is the component that's living in here. So it has to be 0. So this guy's living in there, right? And this is the component that's living in there. And so it has to be 0. Okay, so that's what I've proved what I wanted to prove. Okay. Now let's talk a little bit about cohomology. So recall that on a smooth manifold, the exterior derivative map, right? What does it do? That's funny what I've done now. I think there's only one way to save this, which would be undo, undo. Just leave it like that. Okay. And I'll make another rectangle. Oh, well, let's just leave it like this. So on a smooth manifold, the exterior derivative map satisfies d squared equals 0, right? And so if you differentiate a k minus 1 form, you're going to get a k form. Differentiate again, you're going to get 0. And so we can draw this little diagram here. So when I start with a k minus 1 form and I apply d to it, then I'm going to get into a k form. So this whole, all the k minus 1 forms, when I apply d to them, I'm going to land up there. That's the image of the d map from k minus 1 forms to k forms. On the other hand, we know that when if I apply d again, I'm going to get 0, right? That means that the image of d, which is this part here, is in the kernel, or the image of d going from here to here is in the kernel of d going from here to here. Because if it's something that's in the image and I apply d to it, I know I must get 0, because being in the image means that it's d of something here. And if I apply d to d, I get 0. Okay. But in principle, the kernel could be bigger than that. So the kernel of this d could be bigger than the image of this d. So we can calculate the quotient vector space, right? That's called the de Rham cohomology vector space. So it's the kernel of this d quotiented by the image of this d. Right? That turns out that that gives you topological information about the smooth manifold M. So you can alternatively compute this vector space not using the smooth manifold structure, but simply using the topology of M. And you don't even need to know the manifold structure of M. You just need to know the structure of M up to homotopy. Anyhow, it's a nice vector space you can calculate using, so it gives you topological information about the manifold using calculus, right? And one important thing to bear in mind here is that although I said that not every thing in the image, so the things in the image of D, these guys here, those are called exact forms. So those are K forms that are of the form D of a K minus 1 form. Then it's called an exact form. On the other hand, if I start with a K form and I calculate D of that K form and I get 0, then we say that K form is closed. So the closed forms are in the kernel of D. The exact forms are the things that are in the image of the previous D. And kernel of this D might be bigger than the image of this D. In other words, not every closed form need be exact. Not every closed form need be the D of something. But locally, it turns out that that is always the case. So the Poincaré lemma, so this goes back to the founder of topology, Poincaré. He showed that if you have a closed K form on a smooth manifold, closed in the sense that the exterior derivative map applied to it is 0, then at least locally you can write that K form as D of a K minus 1 form. So locally on a small enough open set U, you can write your K form omega as D over K minus 1 form alpha. The only problem is that you might not be able to say that globally on the manifold, but locally on a little patch, that is the case. If you wonder why that will be the case or how is this proved, just think about you have a small little region. If you have a star-shaped region, then you can integrate it along a curve. And basically what we're doing here is we're sort of integrating. And as long as your region is simple enough, then you can always integrate along these straight lines, going from your middle point to any point you need to get to. But if your region is complicated, then there's going to be holes, and then you'll have to choose which curve you're going to integrate along, and that's going to get you into trouble because you might get different answers along different curves. Okay. So it's not necessarily the case that globally on M, every closed form is exact. So just a quick example, I don't really want to get into cohomology, but it is an important thing to know about. So take S1, the one-dimensional sphere, as our smooth manifold. And I'm going to give you an example of a one form, which is closed, but not exact. So the one form is defined to be the dual of this sort of canonical tangent or vector field, which at each point is just sort of the vector of norm 1 up, going counterclockwise around the circle. I call that del theta. So omega is the one form dual to that. And that's a nice one form on S1. It's definitely closed. Why is it closed? Let's ask the audience. So it's closed because D of omega would be a two form. And you can't have a two form on a one-dimensional manifold because the highest degree of the top exterior power is the dimension of your manifold. So you can't have a two form on a one-dimensional manifold. So D omega is 0 just for dimension reasons. So it is a closed one form, but is it equal to D of a 0 form? So is it equal to D of a function? And I'm just going to give you the intuitive idea of why that's not the case. So this omega can't be the D of a function, because if it was the D of a function, then if I were to integrate this one form around the circle, so that's not something I spoke about a lot, but I did mention it. I said that you can take K forms and integrate them over one-dimensional regions. So if I were to integrate omega over the S1 itself, something I can do because that's a one-dimensional thing, so I can integrate a one form along that. If you write down what that integral means, then you're sort of doing a fundamental theorem of calculus. The integral of a one form is going to be so along a path is going to be the value at the end minus the value at the beginning. Well, the value of the integral of the derivative of a function along a path is the value of the function at the end point minus the value of the function at the beginning point. So since the path begins and ends at P, it's going to be f of P minus f of P, so I get 0. So in other words, if this omega was df, then its integral would be 0 around the circle. But the integral of omega is not 0 because if I integrate around the circle, then I'm essentially calculating the length of the circle, which is 2 pi. Okay, so just to say it in simpler terms, this omega is like is measuring the change in angle infinitesimally as you move along a certain section. So as I move along this section, my angle is increasing by, say, 0.1 pi. And then along this section, it's changing by 0.1 pi. And along this section, it's another 0.1 pi. So if we add up all those contributions as I move all the way around, I'm going to get 2 pi. But that's a problem because if it was d of a function, then adding up the contributions you must begin and end at the same point, because if I start and end at some place, then the total change in the value of my function is just the value of the beginning point minus the value of the end point. So if the beginning and the end point are the same, then the total change in the function must be 0. And that's just the intuitive argument here. So just to demonstrate for you that the de Rham cohomology need not be 0. Although it is locally 0, that's what the Poincare lemma says. So locally, I can write this d as a function, as a d. I can write omega as d of a function locally. That function is indeed just like the angle coordinate, but the angle coordinate doesn't make sense globally on the circle. It only makes sense in a small region, right? Because I don't know what the angle is. This angle of 0, or is this angle equal to 2 pi? That's the problem. So that's why I'd have to like exclude a certain point, and then I can get a well-defined angle on the circle. But I can't get a well-defined angle globally. So just to summarize, the first de Rham cohomology of the circle is the one-dimensional vector space spanned by this particular one form. Okay. So similarly, instead of de Rham cohomology of smooth manifolds, we can talk about the Dolbeault cohomology groups of a complex manifold. Right? Because we've seen now that we've got this refined derivative operator, the Dolbeault operator. And so I can take the kernel, and these guys square to 0 as well. So I can take the kernel of this guy over the image of this guy. Okay, so those are called the Dolbeault cohomology groups of a complex manifold. And there's a similar lemma, which is now saying that locally these groups are 0. So a del bar closed form on a complex manifold is locally del bar exact. Similarly, a del closed form, which is the things that are going on here on a complex manifold, is locally del bar. It's locally del exact. Okay. But globally, there might be some topology going on. However, the difference between Dolbeault cohomology and de Rham cohomology is that de Rham cohomology is not sensitive to the smooth structure. In fact, it wasn't even sensible to the topological structure. It just saw the homotopical structure of the underlying topological space. The Dolbeault cohomology is going to be sensitive to the structure of the complex manifold. So if I were to change the almost complex structure, or if you like, I were to change the equivalence class of holomorphic atlas, I would get different Dolbeault cohomology groups. Interesting, but true. Okay. Here's another nice puzzle for you to think about. I don't know the answer to this, but describe explicitly the holomorphic one forms on the round torus. So holomorphic one forms would be something to be a one form of type 1, 0, which is holomorphic, meaning that when I apply del bar to it, I get 0. Okay, so I'm interested geometrically. I love this round torus here. I know it's a complex manifold. Earlier, I was asking you in the puzzle, what's the nice holomorphic atlas on this round torus? And more precisely, if you have such a holomorphic atlas, you should be able to tell me what its shape parameter is. In other words, then I would describe a isomorphism between this guy and C modulo lattice, and I could extract out a complex parameter tau there. But now I'm asking a slightly different but closely related question. Since I've got a complex manifold, I can talk about holomorphic functions on it, which is what this question was about. Now I'm asking about what about holomorphic one forms? Slightly different question. Describe the holomorphic one forms explicitly. Okay. It must be a nice answer. I don't know it. It's the way that a complex manifold theorist actually defines the genus of a surface. He says it's the dimension of the 1, 0 cohomology group, right? So just to make this clear here. Hope I'm not making an error here, but I think this is correct. To a, shall I call it a complex manifold aficionado, they would define the genus of a one-dimensional complex manifold. So that is a, let's call it a Riemann surface. Remember, that's the definition of a Riemann surface is it's a one-dimensional complex manifold. One-dimensional meaning one complex dimension, i.e. two real dimensions. They would define the genus of M to be dimension of the space of holomorphic one-forms. Which is exactly the dimension of the kernel of the Del bar map, which goes from 0, 0 forms, from 1, 0 forms to 1, 1 forms. And so that's actually the definition. It's not the same as the Dolbeault cohomology groups, but it's this. Okay, but it's closely related. Okay. Anyway, just so that you know. Okay, want to prove one last lemma, then we finish with this section and we can stop. So it's called the I del bar lemma, which is quite interesting. So you can think of it as being a souped up version of the Poincare lemma. Poincare lemma tells us that locally on a smooth manifold, you can write any 2 form or any k form, you can write it locally as d of a k minus 1 form. And similarly, we saw that there was a sort of a Dolbeault version of that. But we can strengthen that in the case when you're starting off with not just any form, but specifically a 1, 1 form. And not just any 1, 1 form, but a 1, 1 form which is closed. Obviously, that's what I want. I want d of it to be 0. And must be real valued. Meaning that alpha was actually a 2 form with real values. So it was actually living in the 2 forms with values in R. So remember that 2 forms with values in R is obviously a subspace of 2 forms with values in C. And the 2 forms with values in C, the complexification of the 2 form space, that's the space that splits up, right? As the 0, 0 forms plus the, sorry, not 0, 0 forms, the 2, 0 forms, the 1, 1 forms, and the 0, 2 forms. So in particular, a good old-fashioned real 2 form on a complex manifold, it's living somewhere in here. And the point of this lemma is to understand where it's living. So in the case when it is closed, I can tell you exactly what it looks like. It's going to be I times del bar phi. So just to be clear, I've got my smooth functions locally on an open set U. Then I can, and then these are real value functions. Then I can calculate its del bar of that. Right? That's going to then give me a so that's going to, since this guy is a subset of the 0, 0 forms, right? Because the 0, 0 forms are the things are just complex valued functions. Okay. So if I apply del bar to a 0, 0 form, I'm going to get a 0, 1 form. And then I apply del to that, I'm going to get a 1, 1 form. And the claim is that if you start off with something here that is closed and real valued, then it can be written as I times del bar phi for some phi living here. Okay. So it's like a double derivative that has been written as, but yeah. So let's prove this. reverse direction. So suppose that I've got a 1, 1 form, and I know that that it's actually, I know that locally it can be written as I times del bar phi locally, where phi is some smooth function on my open set, and which is real valued. Okay, so I'm assuming this right-hand side, and I want to prove that as a consequence, this alpha is going to be closed and real valued. So let's check that. So yeah, what I mean, so I calculate del bar, then I calculate del, I multiply it by I, and I want to check that this resultant thing is going to be closed and real valued. So let's first check that it's closed. D alpha is, well, D alpha is D decomposes as del plus del bar, so it's the same as calculating del plus del bar applied to alpha. So that's del plus del bar. Alpha is, let's get rid of the I, so then I've got del bar phi. So you can see here that I'm going to get out a del bar phi plus del bar, sorry, del bar phi. Whenever I get a del or del bar, then I get 0. So this part here is 0. So that means that the whole thing is 0. This term is 0. And this part here, I don't have a del next to a del or a del bar next to a del bar, but I can easily get that by just interchanging this at the cost of a minus sign. So that's equal to minus del bar, and then I'm going to have a del with a bar with a del bar, and that's going to be 0. Okay. So therefore, d alpha is 0. So I've shown that alpha is closed. Now I want to show that it's real valued. To show that a form is real valued, I just take its complex conjugate, right? Because remember, you've always got this, if you've got this map that takes a P, Q form and gets you out a Q, P form by it's just the taking the complex conjugate, because it's going to send the dz i's to the dz bar i's and the dz bar i's to the dz i's. Okay. So to show that something is real valued, I must just compute its bar. So I calculate alpha bar, and here's the formula for alpha. So I must calculate alpha bar. I'm going to just bar everything there. So I get minus I del bar del phi bar. I don't have to put a bar above the phi because I know that phi is real. So I just took this formula here and I complex conjugated everything. And now I know that this is what? Well, remember, this here is the same as minus del bar. So the two minuses can cancel each other out, so I get I del bar phi, which is exactly what the formula for alpha is. So I've shown that alpha equals alpha bar, so therefore alpha is real valued. Okay. So I've shown that the right-hand side implies the left-hand side. If you've got an alpha of this form, then it's going to be closed and real valued. You might wonder, why do I care about this? Well, the reason is it's going to come up when we study Kähler manifolds. Okay. Okay. So going from left to right, suppose I've got a closed and real valued two-form of a manifold. So I've got a complex manifold, but I forget about that. I just think about the underlying smooth manifold, M, and I've got a two-form on M, which is closed. It's a real value two-form on M, and it's closed. So it's as if I've forgotten about the complex manifold structure. All I know is that I've got a two-form, but now it's the real value thing because I'm forgetting anything about having to do with complex numbers. And I know that d alpha equals 0. And then I want to show that actually I can write that guy in a complex geometric way as I times del bar phi for some real valued function in the manifold. So that's really interesting. Constructing a real thing, which is alpha, starting from a real thing, which is phi, but using complex analytic techniques as a way of getting there. So let's see this. All right. So suppose you start off with a 2 form. Just to emphasize, I've got a real value 2 form, a good old-fashioned 2 form on my underlying smooth real manifold M. So therefore, from the usual Poincare lemma, right, closed meaning, i.e., closed meanings that when I apply the ordinary exterior derivative to alpha, I get 0, right? So locally, if d of a form is 0, then locally it can be written as d of something. So we know that locally there exists a 1 form beta on some small enough open set U such that my 2 form alpha can be written as d of my 1 form beta. Okay, that's good. I'm halfway there. Remember, I'm trying to show, I'm given this guy, and I'm trying to show that it can be written as this. The moment I've shown I've shown that it's sort of a d of a 1 form, I'm wanting to show that it's del bar of a 0 form. I'm halfway there. I show that it's equal to some kind of a derivative of a 1 form. But now, up to now, that's just thinking of the underlying manifold as a smooth manifold. Now I think, hold on, I've got a complex manifold structure, so I can decompose that d as del plus del bar, right? So we can decompose an ordinary 1 form on my manifold, so a real valued 1 form on manifold M. The real valued forms are obviously living inside the complex valued forms, right? And the complex valued forms splits as the 1, 0 forms plus the 0, 1 forms. So beta is, we'll write these components as beta 1, 0 and beta 0, 1. Okay. So what do I know? I know that alpha equals d beta. So that means that alpha is d of this thing. And d is del plus del bar. So putting that all together, I'm going to get alpha is going to be d or del of beta 1, 0 plus del bar of beta 0, 1, del bar of beta 1, 0 plus del of beta 0, 1 plus del of plus del bar of beta 0, 1. Right? So just to be clear, this is a 1, 1 form. Why? Because I'm starting off by assuming that. Okay. So that means well, this guy is living inside the 2, 0 forms, so it must be 0. This guy is living in the right place. So these guys are living inside the 1, 1 forms. And this guy is living inside the 0, 2 forms, so it must be 0. Okay, so I'm now going to refine statement. I know that alpha can be written like this. But more importantly, this equals 0 and this equals 0. So for example, the fact that this equals 0 is telling me we know from the del bar Poincare lemma now, not the ordinary Poincare lemma, but the Poincare lemma for the del Bow operator. that there exists a smooth complex valued function f, so that locally we can write beta 0, 1 as del bar of f, right? F is a smooth function locally on the manifold. Okay. So that's cool. You see what we did? We used the ordinary Poincare lemma to show that alpha is d beta. Then we extracted out the 0,1 component of that. We saw that del bar of that was 0. So by the Poincare lemma for the del bar operator, that guy had to be del bar of something. Okay. Just to finish here, what do we know about beta? We know that beta was a real valued 1 form, right? Because I was just using the ordinary Poincare lemma about real valued forms. So beta was a real valued 1 form. So that means that beta equals beta bar, which means that the 1, 0 component of beta must equal the 0, 1 component of beta bar. Agreed? Right? And so that means that this thing here, or shall I say that, this is calculated here. So that's the same as saying, take the 0, 1 component, which is del bar f, and then I bar it. So that's just going to be del of f bar. So that's cool. I've calculated beta 0, 1, and I've calculated beta 1, 0 explicitly. So that means just going back to this original equation here, I'm able to now write down alpha explicitly, because I knew that alpha was written like this, and now I've calculated those 2 parts. So alpha is del bar del f plus del bar f, where f is some complex valued smooth function on my manifold. And because del bar is minus del bar del, that's the same as del bar of f minus f bar. I think I forgot an f bar here. No, yeah, there. I think I forgot it there. Because I am taking this part here and yeah, I think that's correct. So in other words, I can write that as, well, f minus f bar. F is just some arbitrary complex valued smooth function. So I can talk about its imaginary part. So I can write this as I times del bar of phi, where phi is 2 times the imaginary part of f. Right? Because if you take a number and you subtract its complex conjugate away, then you're going to get out like 2i times the imaginary part of that complex number. Okay, so I proved that alpha can be written like this. Right, so we are now finished with that section from the flock, and next time we can start speaking about Kähler manifolds or possibly line bundles, but I think probably Kähler manifolds first. So yeah, thanks for listening, and I'll upload this to YouTube as well, and also update the notes on the webpage.